The first panelist and presenter I'd like to introduce to you is Dr. Bruce Culleton. Dr. Culleton is Vice President and Chief Medical Officer for CVS Health. CVS is entering the kidney space to not only improve dialysis care, but to change the model by encouraging home dialysis, helping guide and support patients who are eligible for a kidney transplant, pursue that treatment option, and most importantly, focus on early detection and intervention to stop or slow the progression of kidney disease in patients. Dr. Culleton is an absolute advocate of preemptive transplants. I had the opportunity to tour a major research facility with him several years ago and thank researchers who had developed the device that I lived on for 3 years that allowed me to dialyze at home and to keep working. And you can tell from a personal level and from a professional level, he's all in on understanding that patients are intelligent consumers of healthcare, that they can make wise choices, and that patients don't want to end up on disability, that they'd rather stay engaged in life, and if they have a profession or a career, to keep pursuing it. And so it's with great pleasure that we introduce Dr. Bruce Culleton.
Thanks, Paul, for the extremely kind introduction. So it's my pleasure to be here and to describe to you a new business that we're creating at CVS Health. And before I do so, I just want to address a few points and maybe get a couple of slides up. The first is on innovation. And so innovation to me is simply something that's new that adds value. And what you're going to hear from us is an innovative way of thinking about delivering health services in the kidney disease space today. We not only applaud, but fully support the activities that Sandeep spoke about earlier around KidneyX, any future thinking models of kidney care, kidney development, innovation in the space. If we could avoid any future dialysis, then we would be extremely supportive of that. So what I'd like to describe to you today is how we're thinking about innovation today, because we recognize there's a need today to improve the outcomes for patients and to improve quality of life. So I'm going to start with just a little background on CVS. And the reason I'd like to do that is because I'm not sure how many opportunities CVS Health has presented at kidney-related meetings or patient-related meetings such as this. So just a little bit of a background. Before I joined CVS a year ago, I always thought CVS was a pharmacy with a retail store in the front. That was the limit of my education around CVS. That's grown over the last 12 months. So in 1963, actually, CVS opened their first store in Lowell, Massachusetts. This was a retail store. Pharmacy became part of CVS in 1967. And in case you're wondering, CVS stands for Consumer Value Stores. And again, that's something that I also learned over the last 12 months. Over the course of the next 30 years or so, CVS has changed considerably from a retail store and a pharmacy store. And some of those changes that have been instrumental included the acquisition of Minute Clinic in 2006, a PBM called Caremark in 2007, and we have over 10 million members involved in Caremark today. In 2014, the company made a very important decision, changed its name from CVS to CVS Health, and said that we're no longer selling tobacco. And that meant $3 billion, that's right, $3 billion in annual revenue that the company was walking away from. And then in 2017, we announced our planned acquisition of Aetna. And our CEO recently has stated publicly that things are going well, and we anticipate the close of that at some point in the near future. Just a little bit more about CVS. So we have 11,000 clinics around the country. If one excludes the Pacific Northwest, where we don't have too many CVS stores, we are within 3 miles of about 90% of the U.S. population. If you look at the minute clinics, we have about 1,100 minute clinics. And again, excluding the Pacific Northwest, they're within 5 miles of about 90% of the U.S. population. So 5 million people walk through the doors of a CVS store every day. And the reason I'm telling you all that is I just want to give you an idea of the scale that CVS can bring to the table when we start thinking about changing or disrupting the care model for kidney care today. That's really the only reason. So our goal is to make kidney care more accessible, closer to home, and to think about kidney care more holistically, outside of just a model of dialysis. Even though we recognize that's important, but we want to think about it more holistically, more upstream, looking at what's important for patients before and after they need renal replacement therapy. So, in addition to that scale of sort of a footprint across the country, these are some of the services that CVS has today that we feel are, many of which are essential for us to be successful. So we're trying to use what services exist within CVS today to help us be successful as a kidney care business. So I'll start on the right. So you know about the CVS pharmacy. The CVS specialty is here, and I just want to say that we've got a long history of working with patients within the chronic disease space, not the kidney care space, but other patients with other chronic diseases such as ulcerative colitis, multiple sclerosis, etc. We also have a dedicated team, a technology team that works on patient engagement and customer engagement, a very strong analytics group that will help us with our identification of people with kidney disease, and also help us risk stratify so that the intervention is directed at the right patients at the right time. We've made some very big investments in telehealth. We are transforming how we think of minute clinics so that they offer more of a chronic disease service connected to providers and connected to patients through technology. We have a business called Accordant Care, and Accordant Care is a virtual nurse coordination company. So they work with patients who have chronic diseases that are high cost and help those patients navigate through the system. And these are nurses that are specially trained within that disease state. So we're currently working with Accordant to develop a chronic kidney disease model for patients who have kidney disease before the onset of dialysis, so stage 3 and stage 4 kidney disease. And so this is, the reason why a company like CVS is interested in kidney disease perhaps shouldn't come as too much of a surprise, right? So we've heard $34 billion today, and it's actually, I think, $37 billion this year that's being spent on the care of dialysis patients. If one looks at the total bucket of kidney disease, it's over $100 billion that somehow is being spent in caring for patients who have some form of kidney disease. $100 billion. You know that about 500,000 people in this country are on dialysis, and about 700,000 have kidney failure. So there's unmet needs with regards to costs to our system. And this isn't just about saving costs, but it's also thinking about maybe how we could spend that money in a different way. There's also obviously unmet clinical needs, which I'm sure many of you here today recognize personally. Mortality rates are high, 10 times higher than matched controls within the CMS population. On average, a dialysis patient is hospitalized 11 days per year. Now, I can't imagine having to go to hospital. Family members have. I've been in hospital for family members, and it's impactful on the whole family. So 11 days in hospital, on average 2 hospitalizations per year. And the 30-day readmission rate is double compared to matched controls within CMS. So this just isn't a cost issue. This really is an impactful disease, an impactful problem on patients and their family members. Here are some of the problems that are associated with this. So 96% of people who have kidney damage don't know they have chronic kidney disease. About half of patients who have reduced kidney function are not aware of their kidney disease. And about a third of new kidney failure patients, new patients who need dialysis, have received no or little kidney cure before they start dialysis. So the innovation in this area is not necessarily related to creating a new technology. This is really, and I was saying earlier to some people I was discussing, this isn't rocket science. We know what the problems are. We also know what interventions work, but they're not being delivered. There's a lot of focus on dialysis, and there's very little focus on moving upstream. So we also know that there are options, but they seem to be difficult. So access to kidney transplantation is clearly inadequate. So preemptive transplantation, as an example, should be commonplace. In fact, it's rare. We think technology can be improved. It's not just technology that delivers dialysis, but also technology that improves patient engagement and education. And the other piece that, that seems difficult, but again, it shouldn't be, is around home dialysis. So if you ask nephrologists, and I think most of you probably know this, if you ask nephrologists if you had kidney failure, what type of dialysis would you want? 90% plus say, I want home dialysis. Only 12% of patients today are being dialyzed at home. And I need to be very careful here on the in-center treatment model, but I think it's wrong. 4 hours or less in a chair 3 times per week is very disruptive for patients and their families. And that 2-day gap between treatments, we know that creates problems. But that's what we have today. And we spend $37 billion on that. So I'm just going to lay out a new model that we are developing, and we've made quite a bit of progress on. And that new model supports patients throughout the progression of their kidney disease. And on the far left, we are working on systems to help with early identification and multidisciplinary care for patients who are identified with different stages of chronic kidney disease. So we do believe that there are patients who need more education, and that education may be virtual, it may be scalable at a virtual level, and it does not have to be extensive very early on. We also know that if you look at the risk of an individual patient, some patients progress a lot faster than others. We don't always know why. There are markers for why some patients progress faster than others. They're going to need a deeper level of intervention. And that intervention is going to go beyond just being virtual and also needs to be face-to-face. And it needs to be timely. All this means that patients also need to understand their treatment options. They need to be engaged. We need to engage with patients. Again, this isn't, all these interventions, I know Dr. Starr earlier said there's been very little in this space that's been shown to slow progression of kidney disease. That is true. I think ACE inhibitors and ARBs have made a difference. But there are other things that patients can do to lower blood pressure, to look after your health, to have a better diet, to feel better, and we can do a much better job at supporting patients through that care continuum. And then for those patients that unfortunately do need dialysis, that aren't able to get a transplant before they start on dialysis, why should that start in hospital? Why do you have to be hospitalized to start dialysis? Why should you be surprised? our numbers for fistulas that are mature for patients that need dialysis are not acceptable. 50% of patients starting dialysis in hospital is not acceptable. So we really believe there are ways that we can improve that model of care. Again, some of it is through identification, some of it is through targeted management, and a lot of it is through better patient engagement. And then finally, we do believe home dialysis should be more than 12%, both PD and home hemodialysis. We need to figure out a system, not just technology that we're working on, but also a system in how to ensure patients understand the options for their care and work with you so that education is appropriate for patients to better understand your options and increase access to home dialysis. No patient should have to wait 3 months to get trained on PD. And when you're home on PD or you're home on home hemodialysis, your engagement with your healthcare provider should be easy. It should be something that you could do every day if you want to. And that data transfer should be easily accessible to your provider. So I'm actually going to end there because I suspect there's going to be lots of questions. And Paul, I'm happy to answer questions now or at panel.
Yeah. If you could go ahead and take a seat, Doc, and then we'll have our next speaker. But I hope everyone in the audience is getting the sense of the implications of shaking up the status quo. And for those of us who have benefited in life from service provided by the private sector, we're more than grateful. But I think if you take a look at, we were founded 50 years ago, and by and large, the technology that's used in dialysis to keep people alive in that model is 50 years old. And while it's great to take a look at machines that get smaller and then have an iPad slammed on the top, and we call that innovation, as patients, innovation to us is having a modality that we can choose from that matches our aspirations and what our desire to do is as an individual. Not to have it presented to us or dictated to us or have to deal with it by default based on a system that has not evolved to where science, technology, innovation, and patients are in their own mindset. And that's very much what this panel is about. And with that, I'd like to introduce our next speaker. We're pleased to have Michelle Machoka, Director of Marketing and Reimbursement with TVA Medical. TVA Medical has developed a novel system for the creation of an AV fistula in patients requiring hemodialysis. They intend to transform the open surgical procedure into a minimally invasive procedure by using a catheter-based approach.
Thank you. I want to thank AAKP for inviting us to present on our new technology. I'm with TVA Medical. We were acquired about 2 months ago from Becton Dickinson. I'm going to talk about our new way of creating a fistula. So there are over 500,000 patients on hemodialysis. And each of these patients has to go in 3 times a week, 3 to 4 hours, and they all require some sort of a conduit to connect them to the dialysis machine. There are a couple of different options for doing that, but the best option is the surgical AV fistula. And this is a procedure where the arm is opened up, the vessels are dissected out, a vein is swung over and sewn to an artery. Over time, the veins dilate and mature, and then they can use that vein to continually connect the patient to dialysis. Today, this is the best option available for vascular access. It becomes that patient's lifeline. It was invented over 50 years ago, and little has been done to innovate in this space. So today, when patients get a fistula, it's essentially the same type of procedure that they got 50 years ago. Really, nothing has been done to improve this type of access. So it's the gold standard, but it's not perfect. About 60% of these fistulas will fail, so the patient gets the procedure, and 60% of the time, they can't use it for dialysis. When they do work, they take months to mature, and during that time frame, the patient is subjected to a central venous catheter, which makes them at risk for getting infections. Additionally, to get the fistulas to work and to get them to maintain them working, it takes 2 to 3 procedures a year where they have to continually go back into the hospital, have a procedure done to open up the fistula that is shut down. So there's a need for innovation here. We need to be able to make the technique consistent so it's not dependent on the surgeon's skill, which varies drastically from center to center. We also want to make sure that more patients have access to the anatomy. Right now, there are only a few options on the arm, and once a patient runs out of that space, those anatomic options, then they're subjected to a central venous catheter. We've also heard that patients don't want to have surgery, and over 30% of patients just outright refuse because they're tired of having a surgical procedure. And lastly, as we heard from Sandeep, the cost of managing these patients is high, $37 billion, 7% of the Medicare budget, and the increasing cost of the interventions contributes to that cost. So why are these surgical fistulas failing? Well, one of the reasons is the surgery itself, the act of dissecting out the vein, torquing it over, and sewing it to the artery causes a cascade of events to happen that causes a narrowing where they're sewn together, and this causes the fistula to either outright shut down or require multiple interventions to keep it open. So what if we could eliminate the surgery and still give patients a fistula, which is considered the best option? So we invented the WaveLink Endo-AVF system. So this is a system that creates a fistula for patients but without open surgery. It utilizes two catheters that are lined with magnets. One catheter that goes into the vein has a radiofrequency electrode, and one catheter goes into the artery that receives the electrode. The procedure is done by placing two little punctures in the upper arm. The catheters are inserted, and then they're delivered down into the proximal forearm where we create the fistula into a part of the anatomy that you don't typically sew a surgical fistula. So this also creates an additional anatomic option for patients. We deliver a second of radiofrequency energy that cuts a hole from the vein to the artery. We remove the catheters, and now the blood flows into the veins, and they can be used for dialysis in a couple of months. So what are some of the benefits of this system? One, we avoid the scar of the actual procedure. And then because we're creating this in a system in the arm that's deep, where you don't sew a surgical fistula, we get a little bit different of a fistula. Instead of having one vein that you can dialyze from, you have multiple veins that you can dialyze from. And what this does is it reduces the appearance of the ropey arm that you get when you have a vein with all flow going through one conduit. We've also found that this requires fewer interventions to maintain the patency or to keep it open because we're not surgically manipulating the vessels to sew it together. And then lastly, we are giving patients an additional anatomic option, so extending the lifetime for them to be able to have a surgical fistula or another fistula if this one were to fail. So here's what the procedure looks like. There's a small puncture made in the upper arm where we deliver the venous catheter and the arterial catheter. So one goes into the artery, one goes into the vein. The catheters go down into the proximal forearm. They're lined with magnets, and so when they come into close proximity to each other, they will rotate and lock, and then we deliver 1 second of energy with a radiofrequency generator. And this cuts from the vein to the artery. And as you can see, then we remove the catheters, and immediately the blood starts to flow from the artery to the vein, and over time the veins will plump up. We do, as a last step, we coil one of the deep veins to make sure that the veins towards the surface can actually be used for dialysis. This creates a fistula that's a little bit different. You have multiple options to cannulate, so you're not being stuck in the same location every single time. And there are some advantages to that, such as the appearance of the arm. This is what it looks like 2 weeks after the fistula was created. As you can see, there's no scar where the procedure was done. And you can see that the veins are already dilating up and that there are two veins. So you have your basilic and you have your cephalic, so you're not putting the needles in the same spot all the time. And what we're finding is that patients like these fistulas because of the appearance. One, they don't have to have a surgical procedure, so right after the surgery, all you have, or right after the procedure, you only have two little needle punctures, and then here we're showing out at past a year, the arm still looks pristine, so you don't have the ropey appearance of the arm where they're getting dialysis. So very little arm disfigurement. We've conducted multiple clinical studies demonstrating the benefits of the wavelength endo-AVF. Our first study was the FLEX study, and this showed us that it was feasible to create a fistula using this technique, and that we were able to get the patients dialyzed. Our second study, the NEAT study, this was a prospective multi-center study that was powered to a surgical control arm from the literature. And what we found with this study was that we had superior maturation compared to surgery, and we had a lower intervention rate compared to surgery, and able to keep the fistulas patent out to a year. Our third study was the EASE study, and this is our next generation system. So outside the US, we are already on our next generation system, which has a smaller catheter that allows us to go into additional anatomic spots in the arm. Similar results were shown with that. And we're currently conducting a larger post-market study in Europe with 120 patients, and we will be starting a US post-market study in January, up to 300 patients. So what does the data show us? We pulled all of our data from the studies to date for a population of 157 patients, and then we also tracked the acute outcomes from our commercial cases in Europe. And what we're seeing is that we have a high procedure success, 97% in both our clinical studies and in our real-world cases, and this is the ability to create the fistula using this technique. And then in terms of the clinical outcomes, by 6 months, 75% of the patients are able to dialyze on their fistula. And the median time to getting dialysis is 2.1 months. And if you compare this to what we're seeing with surgical fistulas in the US, the last USRDS data was reporting 132 days. So we're able to shave off a couple of months because we're not having to go in and intervene on these fistulas. And then importantly, we've been able to show a reduction in CVC use. So patients who were pre-dialysis at the time of the procedure, only 15% of them needed to initiate dialysis on a CVC, really sparing them that exposure. And at 12 months, the patients who had started on dialysis at the time of the procedure, only 18% still needed a catheter at the end of the year. So what about the durability of this new type of fistula? So when we look at the primary patency, or the ability to, does the fistula need to be intervened on to keep it open, we have a 75% primary patency rate. And then in terms of overall durability, is the fistula open and still functioning? 79%. And this is favorable compared to the surgical literature. But to assess that further, we wanted to do a more robust comparison. And so we used the USRDS database, which is the big database that tracks all of the dialysis patients in the US. And we developed a matched cohort using propensity score matching. And we matched patients based on age, race, gender, BMI, and a bunch of clinical comorbidities, and then also whether they were pre-dial incident or prevalent at the time that they got their fistula. And we tracked their outcomes over a year. We looked at all of the interventions, angioplasties, thrombectomies, whether they needed to have a surgical revision, whether they had to have a CVC placed, whether they had to go in and have any additional procedure done to their fistula to keep it working. And what we found was that at 1 month, already 50% of the surgical patients had to have a procedure, which was pretty astonishing. That's patients having to go in to the hospital, go and have someone take them in, disrupt their life to have an additional procedure already at 1 month. And with the endo-AVF, that number was only 15%. And by the end of the year, 85% of the surgical patients had to have at least one procedure. So imagine going in and you're going to get the gold standard knowing that you're most likely going to need at least one procedure before the year is up. In the endo-AVF group, this was about a third of the patients that needed it at the end of the year. So we saw a significant reduction in the number of patients who needed to have an intervention with the endo-AVF versus surgery. And then in terms of the number of procedures that they need, so the last slide kind of showed you, if you're a patient, what's your risk of needing to have an intervention? The other problem with this is as soon as you get an intervention, you're going to have to go back and keep getting more. And so we looked at the total number of interventions as well, and we found that there was about a 6x reduction in the number of interventions with the endovascular fistula versus surgical fistula, so 0.6 compared to 3.4. So how do patients feel about the endo-AVF? We wanted to understand, what did they think of it? And so we conducted a survey using a qualified questionnaire, the Vascular Access Questionnaire developed by Charmaine Locke out of Canada. And we found that 96% of the patients were satisfied with their endo-AVF, 72% would recommend it to a relative, and 88% found it easy to use, and very few patients wanted to change the type of access that they had. As part of that questionnaire, we also wanted to understand how this impacts their quality of life. And so we asked them to score on a scale of 1 to 5 if they were bothered by certain factors of their vascular access. Are they worried about longevity? Do they have problems protecting it? Does it impact their ability to sleep at night? Does it interfere with their daily activities? Does it interfere with social activities? What about appearance and clotting and bleeding when they're in the dialysis clinic in pain? And on all of these metrics, patients rated it less than 1 or almost less than 1, meaning they were not at all bothered or only a little bit bothered. So this indicated that the endovascular fistula did not have a negative impact on their quality of life. It allowed them to kind of continue on with their daily life. So the Wavelink harnesses patient-driven innovation. We were lucky enough to have a collaboration with AAKP. They worked with us to help us understand what it is that patients are interested in when it comes into vascular access. So we surveyed 150 dialysis patients that had a variety of different access types, and we asked them what matters most to them. And what we found is that patients are most concerned about infection risk, the durability of the access, is it going to last? Are they going to need to go in and have another procedure or an intervention to keep it working? And then how will it impact their daily activities? So in all of these areas, we feel this is a place where the endovascular fistula can actually make an impact on the items that matter most to patients. We also looked at patients who never received a fistula to understand why were they not receiving it. And what we found was that the invasiveness of the procedure and the durability of the perception of the durability of the access were the reasons that patients chose not to get a fistula. And then importantly, when asking patients on who didn't get a fistula, would they have gotten one if there had been a different option? 86% of patients said that if there had been a less invasive option that didn't require surgery, they would have gotten a fistula instead of a CVC. So in summary, we've developed a new technology that reduces the need for interventions, it reduces cost, it improves patients' quality of life, and it gives patients another anatomical option for a fistula. It is now commercially available. We received FDA market authorization in June of this year. But we still have a long way to go. In order for patients to have access to this therapy, we need to figure out how to get it paid for. This past August, we asked CMS to create a new technology APC and billing code to allow payment in the hospital outpatient and ASC setting to really eliminate that financial burden so that patients can actually receive the therapy. We're still waiting for CMS to respond, but we're hoping that with the help of patient advocates, physician community, and the whole dialysis network that we can make sure patients have access to this new option. Thank you.
Thank you very much, Michelle. Now it's a distinct pleasure to introduce another key leader in the field of innovation, a very good friend of AAKP and somebody who's been very inclusive in reaching out to patients, and he'll detail some of that. Our next speaker is Dr. Jeff Lawson, and Dr. Lawson is the president and CEO of Humacyte, and this company is doing very amazing things with bioengineering human blood vessels that could replace a patient's own blood vessels or create a new vascular access for patients who require dialysis without requiring cells or tissue from the patient. And when we talk about leading edge innovation, they're well down the road. And without further ado, I'll have Jeff come up here.
Thanks, Paul. Let's see if we can get our talk loaded.
There we go.
Perfect. Thank you. Good, good. Well, it's an honor to be here and to speak this morning.
As Paul mentioned, I'm going to tell you a story about tissue engineering that we've been working on for about 20 years with the intent of making human blood vessels so you never have to use your own to create a fistula or to have a bypass in your leg. And it's a good long story. It's been a story that started off as a research project academically that's now transitioned into a tissue engineering company to take a technology that was originally funded with basic research and make it clinically relevant. As Paul mentioned, I've been a professor of vascular surgery at Duke University for about 25 years, but have transitioned now to see this technology to its completion and serve as the chief executive officer at this tissue engineering company called Humacyte. And what's important is we're in active phase 3 clinical studies right now. So everything that I'm telling you is research-based, so it can't be viewed as claims with respect to anything that could be perceived as a claim with respect to FDA or European regulatory affairs. So I'm going to tell you a story to try to change this. Michelle was doing the same thing with her innovative endovascular technology, but this is one of my patients. I use it as a point. This is a young man that about 18 months prior to this picture, I had created a well-intended fistula in his left wrist, and you can see that in the sort of right part of the panel. And you can see there's a little vein that's trying to make it. Well, he leaves my clinic and goes and knocks around the healthcare systems in Southern Virginia, ends up getting 6 different interventions on his fistula and 3 different catheter exchanges over the next 18 months, and never has his fistula useful for dialysis and costs the system probably about $200,000. Finally shows back up to have that fistula abandoned and to place a conventional dialysis graft. And I would say that we failed this patient. The whole system failed this patient, and we wasted a huge amount of resource. So what we've been trying to do is actually make blood vessels. I'm, as I mentioned, a vascular surgeon. I'm also a scientist and a vascular biologist trying to think about blood vessels my whole career. And we had a little bit of an ambitious project about 20 years ago with a colleague of mine, Dr. Laura Nicholson, who's a bioengineer and an anesthesiologist, and we thought maybe we could make a blood vessel as the first simple organ that someday could go on to create other organs and tissues. And so about 20 years ago, we started the concept of trying to make tissue-engineered blood vessels and never realized we would have gone through about $400 million of fundraising and about $35 million of NIH and DoD funding, and we're almost there to have it truly be clinically relevant. So what do we do? So I'm going to tell you, and there's a little disclosure here. So most of these are pictures. I'm not going to try to kill you with a lot of data, and some of them are surgical pictures. So for any of you who are, there's some open incisions of people's arms and legs. And just for full disclosure, that's what people go through when they have to have vascular access or vascular repair. So I hope nobody's offended, but there are a couple of pictures in here that you'll see people who actually had to get hurt to be able to get their dialysis care, which some of you know all too well. So what do? Well, we make blood vessels in a relatively, seems like straightforward way. We take over on the left there, you see a biodegradable polymer that we weave in the shape of a tube, almost like the sleeve of a sweater. And if you can imagine that biodegradable polymer that's in a tube can be seeded with vascular cells. We actually get vascular smooth muscle cells from organ donors. And we grow them into a tubular shape over a period of weeks to months in what we call 3-dimensional culture. And we can make those tubes, but what's interesting is if you make those tubes from an individual, they have the antigens or the things that were from the original human that the cells were isolated from. And so to make the tubes scalable and immediately available for patients literally around the world now, we had to figure out a way to take cells from an individual there. That would be, like I said, an organ donor, somebody who has given his kidneys and his heart and his lungs. Well, we take a small segment of a blood vessel when that's happened, isolate the cells from that individual, and grow it in the shape of a tube. Once that tube is grown to completion, we actually remove the cells from the original donor to make this matrix, human tissue matrix, that then we believe we can implant in any individual. And in fact, we've now implanted them in over 400 individuals around the world, and not have a significant immune response. Thank you very much. Let's see if I can, kind of shows, okay. We had to figure out how to make these blood vessels to scale, so you can't just make them one at a time. Initially, we made them one at a time in a laboratory, but we have some really, really smart engineers who have figured out how to make blood vessels in these bags, actually from start to finish. They're grown, that red color is actually cell culture media, and if you can see all this tubing, the cells are actually, to make the blood vessel, you have to actually pulse it. So they're grown under pulsatile conditions because the cells want to think they're living in an artery. And that's the way they make their tissue. And they're grown start to finish in this bag. It's quite complicated, but it's actually wonderful. And we can now grow them to scale where we can make them literally 200 at a time. And we can sterilize this whole process, and I'll show you a picture a little bit later in the presentation, where that bag itself, once it's all cleaned up and sterilized, can be taken right into the operating room. It can be shipped around the world. We've taken it to Europe. We've done surgeries in Israel and all over America. This is actually what the final product looks like. It's a white tube of human tissue. Okay, you can see it looks like a blood vessel. It actually looks exactly sort of like what we would sew into anybody as a vascular surgeon. This is not to get too deep into the science, but this is actually what it's made of. It's made of the same materials that we're all made of. This is human collagen. That's the glue that sticks all our cells together, keeps our skin together. It has the classic kinds of proteins that we're made of, and we've done a lot of other detailed work identifying unique proteins that live in this matrix that we think allow for the tissue to incorporate with your own body once it's implanted and truly become your own tissue. And I'll show you some pictures that support that. This is, again, how it specs out. If you're a surgeon, you care about how it handles. It's got to have good suture retention. It's got to be able to sew like a blood vessel, like you're sewing it into somebody. It's got to be strong enough that it's not going to rupture. In this case, it's physiologically equal or stronger than the blood vessels that we take out of people's own bodies. This is actually what it looks like under a microscope. You can see the surface of it. And if you have to tunnel it or put it in unique shapes, as we do for patients, particularly for vascular access care, you can tunnel and handle it in lots of different shapes. Once we made the blood vessel, we had to figure out how to use it in different animals. And it's hard to do animal work, but you can never do human work if you can't demonstrate something safe in animals. This is a blood vessel that's been used to replace the artery of a dog. And you can see this is the bypass in that sense. We had to make dog vessels for dogs and human vessels for primates, but you can see this out to 52 weeks. We had a human tissue, or not in this case, an animal tissue engineered blood vessel supporting the circulation of an animal in the neck. And prior to our human studies, that's the longest we had had a blood vessel in any animal. As I mentioned, we had to demonstrate not only that you could put these in animals and that they were safe, but actually we also knew with our consultations with the FDA and the European regulatory authorities that they were going to ask us to test this blood vessel first in dialysis patients, as would be appropriate. There's a huge unmet clinical need for dialysis care, as everybody's highlighted today. But we also had to demonstrate that this vessel that we tried so hard to make could actually be safely cannulated. So we had to cannulate it in animals for up to 6 months before we could begin human studies, which is a really hard and difficult set of experiments to do. This you can see the tissue-engineered blood vessel flowing as a dialysis conduit, in this case, in the arm of a primate. Well, this is what it looks like when it's removed. You can see it doesn't have sort of the classic scarring that we see around conventional synthetic materials, but it looks like a human tissue. And in fact, I'll show you some pictures that support that it's grown its own capillaries and truly become the animal's own tissue. It's quite remarkable. This is, as I mentioned, the acellular material. That's a cross-section of it. So you can see there's no cells in there. That's what we made and then what we implanted. And over time, in this case, the animal's own cells, those little brown spots are stained for vascular smooth muscle tissue. And those little holes are little capillary networks that have grown into this tissue, truly creating their own material. What we made as a synthetic graft in the laboratory has now become, in this case, this animal's own tissue. And you can see here it's lined by the vascular cells that are so important to keep blood vessels healthy and keep blood flowing through it. Those are called endothelial cells. But that's the lining that the blood wants to pass through. Well, after doing years, literally years of preclinical work, we finally got approval to begin first in human studies, both in Europe and the United States. And this is the photograph of a vascular access, again, a surgical photograph. That's the venous anastomosis and the arterial anastomosis of a human tissue-engineered blood vessel placed in our first patient. This was actually done in Europe in December 5th, 2012. So we've now had blood vessels in patients for almost 6 years. And after initiating these in Europe, we were able to come back to my institution, Duke University, where a lot of this research was originally started, take that bag that grows that blood vessel into the operating room and literally handle it as it is on the surgical field. If you can imagine this not just as a synthetic graft, but as I like to call it a prematured fistula. We just grew your fistula in the laboratory, had it grow to the right size, and then as a surgeon, all I have to do is put it in the right location to make it work. And this is, in fact, what it looks like, this prematured fistula tunneled under the skin of one of my patients, this young man from Danville, Virginia. And this is what it looks like 18 months after it's been implanted. It looks and feels like a basilic vein transposition. We just never had to get the vein to mature and transpose the vein. Well, we've been able to compile now a pretty significant experience. The first clinical experience, which we reported now about a year and a half ago, was in The Lancet, where we looked at the first 60 human implants that had these tissue-engineered blood vessels. And we were really able to demonstrate some relatively simple things, but they were fundamentally important for moving this technology forward. And as highlighted by these figures, these aren't from the manuscript itself, but we had no evidence of immune reaction, which is really important if you're making a human tissue. People can't react to it like a rejected kidney transplant. So that was the first thing we had to demonstrate. We had to demonstrate that it didn't dilate or fall apart over time, and now we have these, this is out to 300 days, but we actually have it out to 4 and 5 years in some patients, that we don't see these things structurally fall apart. And we've been able to demonstrate excellent flow rates that are appropriate for hemodialysis, in this case, over a liter a minute. If you're going to run your dialysis machine at 500 mils a minute or 400 mils a minute, you got to have high levels of flow. We've also been able to demonstrate, as is shown by the red bars, what we call enduring patency. That means the access that's placed, 97% of them are useful at the first 6 months, 90% are continuing to be used for dialysis, and this is from our phase 2 work, at 12 months, and 75% of them at 24 months. And that really reflects tissue durability and freedom from infection is what we think, is because we don't lose these grafts to infection like you do for conventional synthetic materials. We've been able also to demonstrate in humans, and again, this is a confocal microscopy. It's kind of a fancy technique to be able to look at cells. These are human vascular smooth muscle cells from a human that have grown into the wall of the graft. This is the outer layer of the vessel that has developed the attributes of a human tissue. We call it an adventitia. And it's maybe hard to see, but you can see the lining of the blood vessel developing a natural human lining. The other thing that's amazing, and I think that some of you who've been dialysis patients would appreciate this, but we've been able to demonstrate that this tissue has the capacity to heal. You can see a cannulation track injury in the wall of a vessel or a graft. You see, this is what it looks like for those of you who had ever experienced a PTFE or a synthetic graft. You see those holes? Those holes never heal down there in the bottom right panel. But natural tissues, and one of the reasons fistulas have durability, and we believe that our tissue has durability, is these cannulation injuries heal over time, and the blood vessel has the capacity to heal like we do. Well, just to wrap this up, while we think this is really a very exciting technology, because we're a human tissue, we've had to embark on probably the largest and maybe most expensive clinical study that's ever had to be done in this space. That's what you get for being new. We have enrolled now over 350 patients in our head-to-head pivotal, what's called phase 3 clinical trial. And we decided to do it in 6 countries, I guess go large or go home. So we decided to not only do it in the US, but Europe and Israel, committed to 2-year follow-up. And as I said, 6 countries, and had to do other things that you never contemplate when you're inventing a technology, but that is to bring forward all the manufacturing and quality assurance and vessel release to make something not just be a research idea, but a readily available commercial product. We enrolled our first patient in 2016, and in 15 and a half months, we're able to complete enrollment of a 355-patient study. We'll get the results, the first level of results from that this spring, and hopefully that will allow us to go forward with the regulatory approval to make this material available initially for dialysis patients. Just to come back full circle, we've initiated a second phase 3 clinical trial, particularly head-to-head, not just against synthetic materials, but actually the failure of a natural vein to mature. So we have a clinical study now where patients actually are randomized in the operating room, intent to treat. Either you create a fistula or you place our prematured fistula. And the goal is to see who's off their catheter in 6 months. And if you haven't gotten off your catheter in 6 months, your fistula was probably a bad idea. So we think we can create a human fistula, put it in your arm, and get your catheter out actually in a few weeks. And that's the goal from a patient process of care standpoint. We want to avoid this, which is the sequela of prolonged catheter dependence. And this, again, is one of my patients, and I apologize, but this is the thing that really breaks my heart, is somebody who will be permanently disfigured because she never got off her catheter, because her fistula never worked. And finally, we've always had the ambition of making blood vessels for dialysis patients, but also for everyone else. So we've also initiated vascular repair studies. This is an arterial repair. This is the femoral artery of a patient who has a blockage in his leg. You can see the blood vessel sewn onto the femoral artery, and this is the blood vessel at the knee level, bypassing a complete blockage of the circulation in this patient's leg. And you can see what this looks like at 1 and 6 months. Here's the blood vessel actually restoring blood flow. This is the femur, this is the thigh. This is our tissue-engineered blood vessel restoring circulation to this patient's leg. At 6 months, we now have some of these patients out to 12 and 18 months. And finally, apologize for this picture, but with the support of the U.S. military and the Department of Defense, we have initiated civilian trauma studies. This is our first trauma patient. This is someone in New Jersey who injured their femoral artery in their extremity, and we were able to have blood vessels immediately available for vascular repair and reconstruction. So the surgeon was able to take this patient, injured artery in the leg, open up the blood vessel, and replace it. And that's our goal for our warfighters, is to be able to have injuries in forward operating facilities where there isn't time or logistics to do other kinds of repairs, and have blood vessels immediately available for life and limb. We also have ambitions. We have started a smaller caliber blood vessels. This is, for those of you who aren't familiar, this is a heart, and we know we can do bypass in the heart for those people who need heart surgeries and for children that need congenital surgery. So we can make these blood vessels in larger and smaller and shorter and longer capacities beyond what you would use for conventional dialysis. So just to summarize, we know off-the-shelf bioengineered tissues are possible. We've been making them for 10, 15 years now. They appear to be non-immunogenic based on all our clinical studies so far. They integrate with native tissues. They repopulate with the recipient's own cells. They appear to increase with strength when they're implanted as opposed to decay, and that's because the cells crawl into them and begin to make their own proteins and remodel these as human tissues. And we've been able to do large phase 2 clinical trials in hemodialysis and have initiated programs in peripheral arterial disease and vascular trauma. And we've completed enrollment of initial phase 3 clinical trial. We have a second ongoing phase 3 clinical trial again to test the concept of improving fistula creation. And we have other cardiovascular programs that are significantly advanced and well into development. And we think that this kind of technology will be the platform of being able to make vascular tissues that will sometime be able to transition into something to really grow a kidney someday. So we're optimistic that this is a platform technology that someday will be used by others to make all kinds of things. We're starting with the simplest organ, a human blood vessel, but we think that that will be something that will be a platform for others to go forward and someday make kidneys or make hearts or lungs or eyes or all the things that we know are possible because they're made in the wombs of pregnant women around the world every day. We just need to understand how it's done. So with that, I will thank you and be happy to take any questions.
So literally, Doc here came in from a visit in Paris, right? And we appreciate your timing, perfect timing. But 2 key points after that presentation. We talk a lot about the federal government. A lot of people think, hey, nothing's happening in the space. There are great things that are happening. There are a lot of agencies. There are the obvious ones. There's HHS and the many different agencies, sub-agencies within HHS. You saw labor here today. Doc has just talked about the role of the Department of Defense. You have the Veterans Affairs Department that's also engaged in this. Later on this afternoon, you'll meet one of our new AAKP officers, our secretary, Ed Hickey, who also serves as the chair of our Veterans Health Initiative in working with the VA, and some past associations with leadership at DOD, who will be very active with AAKP here. Ed's a Marine. Dave is Army, and we have another Army vet around the corner here. But you'll see that what it takes as a patient advocacy organization are connections and being able to understand that a federal government has many different cabinet agencies that bring many different resources to the issue of kidney disease and to innovation. Our goal is to educate folks on where the barriers are and to get folks to work across silos. And so that's what the point is here. What we'll do is we'll go ahead and do some questions and answers before the next panel. Again, this is facilitated questions, so you can go ahead and pose the question. I'll need to repeat it because we're taping, and then we'll move right along. So for the first question, see a hand? Great, go right ahead.
My name is Melissa Bensuda, and I'm a part of the $37 billion ESRD expense per year, and the 12% home dialysis patients. I've been on home dialysis for about 12 months. First, wanted to thank you for the innovations. It gives patients like me hope. I've had the same fistula since 2002. I've been very fortunate, but I know it won't last forever. I do have a question for Dr. Colton. So I'm really excited to see where CVS is being innovative. I'm curious as to the patient expert involvement as you're building out products and services, how involved patients are.
So to Dr. Culleton and CVS, a question from a patient and one who's taken the journey and knows it quite well from the slides that have been up here. But in terms of patient engagement, what is CVS doing to step up to the plate, engage patients at the front end and through the process that you just outlined?
First, I think we can do better. I'll tell you where I think we're reasonably good, and then I'll tell you where I think we can do a better job. And maybe that's where we can also work with you on figuring some of the stuff out. So I think on the technology side, not just on the device technology we're developing for home dialysis, but also on some of the other connectivity technology that we're working on. We actually do a really good job at getting patients involved early on before development in trying to understand patient needs, and then throughout development through informal or formal testing of what we've developed. So I think in that sense we've done a pretty good job, but we can always do better. The area where I think we can do better, and that is around services and understanding as we're developing our services model, what's most important to patients. And so I think that's something that we can certainly progress, do better in the future. But thanks for the question.
Great. Thank you. Next question for our guests. Right up against the back.
This question is also directed to Dr. Colton. My name is Patrick G, and I was a PD patient for 4 years. What is your approach or focus when it pertains to home therapy patients in the event of an emergency? As far as getting resources or working with groups like CASER and other nonprofits to be able to, for patients to have access to medication in the underserved communities that may be in the midst of emergencies or natural disasters.
This is a question for Dr. Culleton from Patrick G., our new board member out of Richmond, Virginia, and the question is quite timely. So as we move towards home-based care and the prospect of being able to have patients better connected and able to do care that keeps them employed and more mobile in their communities, in the event of a disaster, a Katrina, a Wilma, issues that we've recently seen in the news, what's the planning process for you in an adverse situation, and how are you engaging patients along that line?
So, Patrick, that's a timely question. And I would say that we are still working through the details, but I will tell you how what we're going to build upon and who we're engaging with. So you could imagine that given our store locations and the pharmacies that are located within those 10,000 plus stores, that we've become accustomed to making sure that patients who rely upon their pharmacy for their medications have those medications during periods of natural disasters. So this is, we're a company that's been doing this for a while and understand that the needs of patients and their need to get their medications. We have processes in place to look after that. And for the most part, a lot of that comes down to understanding when patients need their medications, understanding when a disaster may come, and many times, at least in this country, they are predictable, and then reaching out to patients and ensuring that they've got their right access to their medications. So we could certainly build upon that process when it comes to us actually being a home dialysis provider. But work to do. Keep in mind that we are not a home dialysis provider today, so we recognize that there's still a lot of work that we need to do to support patients in the home. The other piece is we also have started engagement with the Department of Disaster Preparedness, and we've had several discussions with that department within Health and Human Services. We think we can help there too.
Great. Thank you very much, Doc. Next question. Great. This question is coming from Bill Muldoon, a board member of the Kidney Health Initiative.
Jeff, as a fellow entrepreneur, I know that besides the science regulatory path, you have to secure capital to move your innovation forward. How did you do that, and any lessons learned?
The question is to Dr. Lawson, and the question is in regard to capital and innovation. And probably a timely one for Dr. Lawson, who is a great entrepreneur, a compassionate caregiver, and somebody who understands that it takes private sector funds to make something happen. Go right ahead.
It's a great question, because you can't do transformative things if you can't fund it, right? You can have all the great ideas in the world, but if you can't find resources to support them, they'll never get done. We've been very fortunate. Initially, we had very good support from the NIH, the American Heart Association, and the Department of Defense. So you can get things pretty far along to actually form a good idea and a good company, and you have to have that investment. And in fact, it's been a wonderful investment. But at some point, you got to convert it into a real company that's going to make a real thing. And so we've done now 4 rounds of fundraising and raised over $450 million of capital to build out a manufacturing facility to do global phase 3 clinical trials. That's a huge investment. You know, when you start thinking about the Kidney X project, trying to make a kidney, we're $500 million in trying to make a blood vessel, and 20 years. I mean, it's been like the arc of my and Laura Nicholson's entire careers. But you have to be able to have a good story, a compelling story to have something be transformative. And, you know, there are people and there's capital out there that are willing to invest in a good story if they think it's going to potentially change the way we do healthcare. You know, we're trying to make the first human tissues that we can implant in people. And if you can make that a compelling argument, I think you can raise funds. So we've been very successful in raising private funds. We haven't gone into public capital markets yet, but at some point that will likely happen if this company is really successful. But we still have to get something finally approved, and you know, this is how long we're in. We formed the company in 2004. First human implants are almost 6 years now, and we're still not approved to have something commercially available yet. So it's a long run, and it's not for the faint of heart.
Thanks, Doc. Next question, Richard Knight. Richard Knight is our vice president and our incoming president of the American Association of Kidney Patients.
Thank you, Paul. Michelle, I have a question for you. Very interesting, innovative advice that you have. I know that you're a little bit smaller company, and you've now been acquired by a larger company. How has that helped your organization in terms of your prospects of being able to get your product out?
So the question is to Michelle, and it's from Richard Knight, and the question is, as a smaller company who was recently purchased, how has that been able to help you get your product out with that investment of capital and with all of the apparatus that comes with a large purchase like that?
Yeah. So we were acquired about a week or two after we received FDA approval, and having the backing of a larger company has been really beneficial. As Tiva, we were 20 employees and we wore multiple hats. And if we had to go commercialize this on our own, it would have been nearly impossible to be able to reach all of the patients in the various areas. And so having the backing of a large company, now we're able to develop a training program to make sure that we deploy it properly, train all of the stakeholders from the surgeons, the nephrologists, the cannulators on the full spectrum, and then also have the support to roll it out properly and make sure that it goes into the right hands. So I think it's been helpful. We also have additional resources to help on kind of the reimbursement, and that's our next big hurdle is the reimbursement front. And I was wearing the reimbursement hat beforehand, but now we have a whole team of people that can help us. And so I think having BD come in has been beneficial for us and ultimately for patients because we'll be able to have a greater reach.
Just one additional comment. You know, I think something that I've seen, not just with our own program at Humacyte, but lots of technologies that I've been involved with. You know, industry, big companies used to do R&D, and they really don't do that much R&D anymore. They let other people do it, like Michelle, until everything is sort of de-risked and approved, and they'd rather pay more for it at the end when they know it's going to work. And so they've kind of killed their own R&Ds, and they let it sort of work through small entrepreneurial people who figure out how to make it work, and then they just grab it once it's done.
Thanks, Doc. Next question. In the back.
Having a fistula for 25 years, over the years, that thing is larger. So is this thing going to stay the same size, or after, you showed one at 18 months, but over a period of 10, 20 years, is it going to stretch out also as the natural ones do?
So this question is from Dan, who's our treasurer. Just kidding, Dan. Dan is our secretary for AAKP and a board member. And he is the money guy, actually, behind the scenes. But his question to you is, as a practical experience as a patient, is it going to get bigger? What's the practical impact over time?
So Dan, it's a great question. It's one of these long-term durability kind of questions that you can only answer over time. We know that fistulas, I've spent sort of my academic life trying to understand independent of making blood vessels, understand when they dilate, when they don't, why they scar down. So we don't understand why fistulas truly become aneurysmal over time, but many of them grow quite large for probably many reasons, but it has to do with outward remodeling of native veins. Our material appears to stay somewhere between 6 and 7 millimeters in diameter, kind of the size of your little finger, over time, where we've done serial ultrasound. So we, in clinical studies, sequentially ultrasound the material, and it appears to have the sort of same size durability. We haven't seen a lot of evidence of it dilating over time like we have seen with other kinds of tissues, what we call them xenografts. I don't know if there's some porcine vascular material or bovine vascular material that does appear to dilate over time, and that's because it doesn't have the capacity to heal and remodel because it's a fixed foreign tissue. To date, we haven't seen that with our material, but we won't know until we have it in someone for 10 years and have it in lots of people, because there may be some people that it does dilate in because of their own kind of unique biology. And that's something we have to watch for responsibly. We'll have to follow with patients for many, many years and look for infection. We do know that the vessel can be injured. We've seen people with large balloons be able to rip the vessel. There's a lot of radiologists like using large balloons. It's a long story. But and so there's some care that comes along with a material like this that we're learning about as we get larger clinical experience. And that's part of doing big clinical studies in real world experiences. But it's a great question. Thank you.
Okay, to follow up with that would there ever be a need, could it be taken out, or would there be a need to take it out?
And a follow-up question to that, Doc, is can it be taken out, or would there ever be a need to actually remove the vessel?
So, having now 300 or 400 human implants, there have been occurrences of surgical revision for different reasons that happen with dialysis patients. Many of them have to have different kinds of procedures. So we have gotten samples of blood vessels that have been removed that we've been able to study. We don't routinely take them out. Many of you who maybe have been patients who've had access, if you get a transplant, we usually leave your access in place. And usually the only time we put someone through the surgical morbidity of removing their access is if it's infected. Because if from a surgeon, and when you see the wound care associated with it, removing the access is actually more morbid than leaving it in place. So our intent would be the standard of care, which is if it's fine and you go off dialysis, we'd probably leave it in place. If for some reason, compelling reason, you wanted to have it removed, it could surgically be removed. But we usually don't recommend that unless it's causing you a problem with your circulation or it's infected. And to date, we haven't seen that occur.
Okay. Great. Thank you very much. I'd like to thank our panelists. I'd like to point out that Dan Abel with the AAKP board, his background is as a patient. He's been very involved in kidney care over the years. But the other thing is you're hearing a patient who's a business person, an employer, and an innovation leader in business in West Virginia asking a practical question. But much of Dan's life has been dedicated to making certain that patients are well educated and that for people that want to pursue a career and be a business person or capture their dream, they can do that. So these practical questions about how things actually impact them are real because our patients have experienced them. And for that, we thank you. Thanks, Dan, for the question.